over to Kevlin. Get it right.
Okay, so awesome. I'm not getting good feedback from GoToWebinar, so can somebody confirm that what they see on the screen currently is 6 impossible things against a black background?
I can see it.
You can see it. Excellent. Right, that's all I need. Excellent. Right, let's go. Perfect. So this came about. This came back because I quite like numbers. I edited a couple of books with the word 97 things in the title. I think my most popular talk on YouTube is called 7 Ineffective Coding Habits, or along those lines. I wrote a blog piece many years ago that mushroomed into a talk with Frank Bushman, my co-author, called 5 Considerations. And I also, for a period of years, ran a workshop called Programmer's Dozen, based on 13 recommendations, 0 to 12, for coding guidelines. And so I am naturally drawn to having numbers in the title. It's always an interesting challenge. It's in one sense, it kind of goes against the advice of don't hard code numbers into your code. So yeah, it's kind of fun to play with. And this one, 6 impossible things, emerges well. The origin of this is Alice, or Through the Looking Glass and What Alice Found There, by Lewis Carroll, and her conversation with the White Queen. And the White Queen says, sometimes I've believed as many as 6 impossible things before breakfast. And that idea, the impossible things, also, I guess I started off with Richard Feynman's 6 Easy Pieces in my head, and then I started thinking 6 impossible things, because I'd noticed a number of things that people often get drawn into without meaning to, but thinking habits or assumptions. Okay, an assumption is not even a thinking habit. It's beneath that level. An assumption is a thing that you do not really know that you have in most cases. So, for example, when people are, I guess this is the 7th impossible thing, when they, I've seen projects have a page that says list of project assumptions. I have to laugh at that, because the one thing that you cannot know is your list of assumptions. If you said current list of known assumptions, then I'd be right on your side. But the point is, you cannot state your assumptions in advance, because by their very nature, an assumption is a thing that you don't really know until you've stepped on it. It's a bit like a Lego brick, stepped on barefoot in the dark. You know you have assumptions, but you can't easily quantify them until you actually have encountered them. And they are normally demonstrated by contradiction. You learn you have an assumption when it is contradicted. Oh, I had assumed that. And we see this all over the endeavor of software, whether we're talking about code, working with APIs, whether we're talking about what a client is doing. And so we'll get to the unknown unknowns. It's possibly the only contribution Donald Rumsfeld made of any use to Western philosophy, or indeed Western civilization. So let's try number 6. Let's do a countdown. Representations can be infinite. Now, some of these things are really obvious when you state them. Yeah, of course, this is not possible. Yeah, but we kind of flirt with it, and we have blind spots. You know, we say, well, you can't have infinity. Yeah, sure you can. The standard IEEE 754 representation of a floating point number allows for plus and minus infinity. You know, so I can represent infinity, but that does not mean that a representation can be infinite. We also have other concepts of things that are non-finite. For example, NaN is a particularly popular choice for the web generation. You know, back in the days when I used to actually be able to fly and book flights, this was something I used to see every now and then. And I love the kind of the self-referential observation that the JavaScript says, try to parse but NaN, but it is not a number. Exactly, how insightful. But it has got to the point where there's a whole generation of developers who now think that NaN is something to do with JavaScript, whereas it dates back to the 1980s, and it's a feature of a floating point standard, not a programming language. To the point where this was an interesting one. This happened last year. Driverless race car drives straight into a wall. during the initialization lap, something happened, which apparently caused the steering control signal to go to NaN, and subsequently the steering locked to the maximum value to the right. And I remember this is brilliant. Basically, it had done a trial lap, and it just went straight into the barrier after it started. We can have interesting conversations about statefulness, error checking, and all kinds of other stuff. But one of the comments I got on Twitter when I retweeted this is somebody said, "Oh my goodness, people are programming driverless cars in JavaScript." So no, NaN is not just JavaScript. This one was actually MATLAB, but it is very much, kind of the aspect we see on the web in many cases, and it does make me think that we should call these Batman bugs. But there is a deeper point here. We find that when we deal with, let me think. So hang on, I'm just looking. Chris, you asked a question. IEEE 754. I think that was my statement. So I think I'm going to consider that one answered. So let's talk about this stuff. Let's mess about with these numbers. First thing that we have to do, in fact, the origin of this book I edited just over 10 years ago, funnily enough, was a floating point issue. It was a piece of code that I'd seen, a client had sent me, and I just said, "Oh, damn it, that's just one of those things that every programmer should know." And I happened to know there was a 97 Things series, and I thought, you know what? That's a really good idea. Maybe we should have something that every programmer should know. And I also had in mind a person. Most of the contributions were just straight out of the blue. Some people I prodded, but one person I did actually approach very specifically to write a piece because he had written a whole load of stuff. A guy called Chuck Allison, a professor in the US, who I knew through various committees and things. And he'd written a whole load of stuff on IEEE 754, and I had a title for him, basically. So it's the only person I went to, and I said, actually, I don't just want you to write a piece, I want you to contribute a piece with this title. Floating point numbers aren't real. We fall into this trap. But what I really loved was the way that Chuck pointed out, real numbers have infinite precision and are therefore continuous and non-lossy. Floating point numbers have limited precision, so they are finite and they resemble badly behaved integers. Now that characterization, I love that one. I've used that one ever since when talking to people. It's just like, yeah, watch out, floating point numbers, they're just badly behaved integers. Now, how badly behaved does that need to be? Because it turns out integers are incredibly badly behaved as well. So a few years ago, I had this little error message from Visual Studio telling me that my license would expire in 2 to the 31 minus 1 days. Curiously suspicious number there that suggests that something was not correctly initialized and modified. But the thing that I guess is a little perplexing, I mean, I think I'm fine for my lifetime, and indeed many lifetimes. Your license has gone stale, it must be updated. No, it's good for quite a few days from what I can tell. But this idea that representations can only be finite in some sense, it's obvious, except that's not what people think, particularly people who fall into the trap of thinking that programming is mathematics. Now, it is certainly mathematical, and I can certainly encode it, but when most people say mathematics, what they are normally thinking of is the stuff that they did at school, or if they come from an engineering or applied science background, they think of that mathematics. That is totally not the mathematics that computers and programming languages do. This is one of those discoveries I had when moving into computers. Having done a numerate discipline, I then moved into the innumeracy of computer science. And it's such an assumption. It's so ingrained in us that even when we know it, we forget it. So there's this nice, there's this piece by John Bentley in Programming Pearls, published in 1983, Writing Correct Programs. And he even wrote a paper on how to write a correct sort algorithm. And the most important, how do you know it's correct? Because he proved it, because it has a proof. And the particular example he has here is the challenge of binary search, because it turns out most binary searches, sorting algorithms and so on, well, maybe not most, but a ridiculously high proportion of them have a bug in them. And so he set out to prove this. And this became a very widely used algorithm. He was also a professor of computer science, and Josh Block's Josh Block was one of his students, and Josh Block implemented the Java collections and algorithms back in Java 1.2. So here is Java's as it stood when it was introduced. This is binary search. It is based on Bentley's algorithm. This is what Josh Block implemented, and this is all fine until you introduce a very large array. And it turns out that this is a problem, because it turns out that ints are not integers. They are a subdomain, and they have some interesting wraparound behaviors. They don't do saturated arithmetic, which would be the alternative. Is once you hit the top, you're at the top. They do modulo. They have modulo behavior, and it turns out that all the identities that we learned at school, such as a plus b divided by 2 is equivalent to a divided by 2 plus b divided by 2, and all these variations of this are absolutely false when we hit most programming languages. So this was not a problem back in the 1980s, because when you're trying to find the midpoint, the mean between two numbers as you are binary searching, you are never going to hit memory. You're never going to hit a size for a 32-bit integer. You're never going to hit a size that you could actually hold in memory. It was only as we started nudging into the larger memory of gigabytes that this became an issue. Once we got a few hundred megabytes back in the 1980s, not a problem. Back in the 1990s, not a problem. 2006, yep, this is a problem. If the number you are searching for, you have a very large array, if the number you're searching for isn't the upper end, then it turns out that low plus high wraps around to a very negative number, and this all goes to hell. So you end up with a correction like this. If you are looking at this mathematically, you will simplify it to this, which is wrong. Back in 1998, this is the USS Yorktown, which has since been decommissioned. It's a US Navy cruiser. It found itself kind of quite literally stuck at sea. Actually, I think it was stuck in port over the weekend. Basically, they'd upgraded their system to Windows. I should put upgraded in quotes. They upgraded their system to Windows. And for those who enjoy the idea of military software being less reliable than actually commercial software, you'll be delighted to know the use of Windows. The Royal Navy used to, in fact, they probably still do, because they're not exactly up to date, on the nuclear submarines, which are obviously entirely safe. They use a variant of Windows, or used a variant of Windows that was known as Windows for Submarines, which kind of tells you everything you need to know about safety. And it turns out the problem that they had, source of the problem on the Yorktown, was that bad data was fed into an application running on one of the 16 computers on the LAN. Normally we think that that's fine. The data contained a 0 which shouldn't have, and when the software attempted to divide by 0, a buffer overrun occurred, crashing the entire network and causing the ship to lose control of its propulsion system. I believe that this data handling would have been in a driver, because obviously if this is in regular app space, that's not really going to be a problem. You just crash an application rather than absolutely everything. So the point here is we don't have infinite representations. We have an idea of unboundedness that often traps us, that things can go on forever, that a file can grow forever, a database can grow forever, that a video can stream forever, that these things are indefinite. And when you translate unbounded and indefinite into another form of English, you end up with the word infinite. And we should know that that is not a thing that we can do on a finite computer. And that if we do not specifically handle it, the universe will hand it back to us with a slight hint of laughter in the background. Every question has an answer. This sounds like one of those things that you sort of have with kids. So the idea that whenever I make a request, whenever I call a function, whenever I want something, there is a response there. So I'm going to take you back. I'm going to take you back quite a long way here. This is an error message I got from using Facebook. It was not, hey, guess what? Your democracy has been corrupted. This was a slightly more modest one. I'd submitted some usability or bug issue because I run a couple of pages on Facebook still, and there was a bug, and I thought, you know what, let's report that. And I was told that my feedback would be used to improve Facebook. That clearly has not happened. Thanks for taking the time to make a report. And the amount of time it's taken actually predates the existence of Facebook or indeed any of the infrastructure that it relies on. 31st of December 1969. That's kind of an interesting number. And the point about all of these numbers, like 2 to the 31 minus 1, is whenever non-software people see these numbers out in the wild, and you know, we need to remember that software development is responsible for most of the installation art, the accidental guerrilla installation art on the planet. As people walk around in the streets, whether it's advertising signs, whether it is things in bus stations or airports, or signs telling them when the next bus is going to be, there's this kind of guerrilla accidental art of error screens. Many people look at these things just thinking there's an error or not understanding them. People who are in software development understand their significance. 31st of December 1969, that seems familiar, or really close to familiar. The time function, so the IEEE standard for POSIX, which is basically the standardized version of Unix, standardizes the meaning of the standard C time function. C standard is not required. The C standard is required to have a time function, but it's not required to do what I've got on the screen. The time function shall return the value of time in seconds since the epoch. It's not required to do that in standard C, but I'm not aware of any standard implementations that don't do this. Everybody takes the POSIX implementation, the POSIX epoch as their cue. That is date 0. 0, that kind of feels like something that might be accidentally initialized or mem set over. In other words, we have zeroed memory. And when is the epoch? Well, it turns out that this convenient set of driver updates from Intel, apparently they had driver updates available on the internet at midnight on the 1st of January 1970. I suspect that this is not correct, but that is the epoch date. So if you zero your time result, if you use that variable, the time t variable, with 0, that is when it is. So how do we get 31st of December 1969? Well, Anil Dash made this wonderful observation a couple of years back. The natural enemy of the program was the time zone. If you take epoch, if you take where I was, GMT, if you take where I was and then you shift it to California, then that takes you west, which takes you from midnight, the new year, the 1st of January 1970, that takes you back into the 31st of December 1969. So that's one explanation. I used to be quite keen on this, but digging around, I was looking for something else. Digging around, I started realizing, you know what, there's another explanation here. -1, you only have to be 1 second before midnight. -1 is actually more plausible. 1 second before midnight, and it's 31st of December 1969. In other words, it wasn't something was incorrectly initialized. It's that not every question has an answer. If we go and look at the C standard, the value -1 is returned if the calendar time is not available. That is an interesting one. It is most likely that this happened, that there was a call to time and the time was not available. And we automatically think, oh, time is available around us. It's not. And this has consequences for the way that people think about testing as well. They often assume that they forget that time is a resource, and the time, the concept of system time. I'm looking around my office. I've got 4 different sources of time. The idea that you have one source of time is kind of sweet and really not what proper grown-up programmers should be thinking. You have multiple sources of time on your computer. You have what is reported by any given API that you choose, or what is reported by the network. That's at least 2. So the idea of the time doesn't make any sense. You have to choose your source of time. But that also tells us, what if I want the time and it is not available? In the real world, again, we would make the assumption the time is not always available. Okay, if I ask somebody, hey, have you got the time? And they said, no, I haven't got a watch. I don't wear a watch, for example. I have a phone, but occasionally I forget my phone. It's a very uncomfortable feeling. I don't recommend it. But the idea is that time the information about time not being available is something we are used to in the real world. We're not sure what time it is. We might have to ask somebody. The idea in code that time is always available, that it's a system service. There is no requirement that all operating system services are always available 100% correct. We want them to be correct, but that's not the same as they're actually there. That question may not have an answer in the domain that makes sense, or rather when it tells us, hey, guess what? I'm sorry, I don't have the time. By using an integer to signal that, well, unfortunately, we've just ended up back in 1969. Now we might say, oh, that's an artifact of integers. You're going to get it with all kinds of things. But there is a deeper aspect in which the observation about not every question having an answer has consequences. So many people kind of relate to the idea of, or get tired of the idea that computer science is often anchored in algorithms. You know, it's what people might remember from classes. Yeah, it's all about algorithms. So what is an algorithm? Well, it's important to kind of define this because the word algorithm comes in for a lot of abuse these days. I'm forever reading about the problem with various companies' algorithms and machine learning algorithms. There isn't a problem there. The algorithms are quite straightforward. They're basically stats. They're basically matrix multiplication with a little bit of architecture thrown in. The algorithm is not the problem. It's the configuration that is the problem. The configuration that we have no idea how to read. And oh yeah, we use training sets. We have data sets. We have large data sets. It's not the algorithm. It's the data. So that's where many of the problems lie. So the word algorithm has become devalued, but it has a very precise meaning. As indicated on screen, a process or set of rules to be followed in calculations or other problem-solving operations, especially by a computer. Now, there's an interesting but subtle distinction between the word algorithm and the word procedure. Most people aren't aware of the distinction because, quite frankly, it doesn't matter. But there is one. All algorithms are procedures, but not all procedures are necessarily algorithms. The main difference is that the procedure can halt or need not halt. An algorithm must always terminate by definition, otherwise it is not an algorithm. I mean, you can call it an algorithm that doesn't terminate, but that's actually called a procedure. An algorithm that does not terminate is an algorithm that does not yield a value. And we can also find other cases where we've got this idea of, well, I don't have an answer that can be expressed in finite time. We're back to infinities again. So given that we're dealing with data structures and algorithms, well, rather we're dealing with algorithms, let's go for data structures. Let's deal with one of the kind of classic data structures, a stack. Represented here is a set of links. So I've got 4 links, singly linked list, and null or nil at the end, and I can push onto it and I can pop from it. Now, this seems fairly straightforward. Thank you, Imo, for the Douglas Adams quote. All Douglas Adams quotes are always appreciated. Time is indeed an illusion. But as developers, we get to fabricate our own version of time, and lunchtime doubly so. And we also get to fabricate long lunch times, but we're not very good at doing that. We often work through them. That's a bit of a mistake. So this is a very conventional way of looking at a linked data structure, but I want to look at it slightly differently. I want to look at it as a process. Let's deal with time. So what I'm going to do is I'm actually going to say I'm going to have a running process, and I'm going to say I've got a push channel. So this is some Go code. I'm going to have a running process, and I've got a channel for pushing, and I've got a channel for popping. So on the push channel, I send things. On the pop channel, I get values back. Okay, so whatever happens in the process, what happens in process stays in process. Specifically, this is a Go routine. I'm basically taking a stack function, and I am running it concurrently with the code that you see on the screen. I'm giving it these 2 channels here, push and pop, and that's how I'm going to communicate with it. So I'm going to push 1 potato, 2 potato, then I'm going to pop 2 potato, 1 potato, and that all works really nicely. Now, what happens when I go back a bit and say, okay, well, what am I expecting if I just create a new one that is empty and I pop from it? Now that's kind of interesting because I'm not expecting an exception because there's no way to throw exceptions. Well, Go doesn't have them, but that's not meaningful. I've got 2 ways of communicating with something. What am I expecting back from it? We could go for the -1 option, as it were. I'm going to say that's not a good idea. But what we've got is nothing. What happens when we pop from this? Well, we could try drawing up a state model and say, well, how do we reason about this? And currently, as our state model is expressed, we create it, it's empty. We push, it becomes non-empty. We keep pushing, it becomes even more non-empty. And we can pop when we're non-empty. And for as long as the number of pushes is greater than the number of pops, we remain non-empty. The moment the number of pushes equals the number of pops, we become empty. And if you look at the empty state, there is no transition for pop. In other words, the behavior is undefined. This is a minor point for those who care about notation. This is a Horel state chart. It was incorporated into UML. It's probably the only bit of UML that's actually really well defined and used. There's 2 bits. But one of the most important things people misunderstood is that people think, if a transition is not specified, it defaults as a self-transition, remaining in the current state. And that was kind of in part propagated by Martin Fowler's UML still, which got this one wrong. Specifically, it's actually undefined. Quite literally, this behavior is not defined. So let's go and have a look at how we might implement that and what the consequences are and what this means for termination. Here's my stack. It's a function. It's got a push channel and a pop channel. Nice directional arrows indicating what we're expecting. We're actually going to hold the internal representation as an array, and then we're going to loop forever. And we're going to say, okay, if the depth is 0, we are empty. So therefore, we are prepared to take a push. And we will append it. Otherwise, we're not empty. And when we're not empty, we can either take a push or we can do a pop, and we can pop that back to the caller. Now, it turns out we've got another way of representing this. The observation that to iterate is human, to recur is divine, means actually we don't need an intermediate array. And this solution is probably a little more familiar to people who've stumbled across Erlang. I'm going to use the call stack. I'm going to use recursion. I'm going to basically start off my stack, and I'm going to repeat it. I'm going to loop forever with respect to a non-empty stack. And what we're going to do here is we're going to wait for a push. And this is our empty state. And then the function that we call non-empty stack, we can take push and pop, and we take the value that was pushed, and we keep that as a local variable. And then we're available for pushing and for popping. And if we get another push, then we recurse again, and we keep the new value as our local value. In other words, we use the call stack to be the stack. And when we pop, then we just quite literally pop, we return. We have our local variable is returned to somebody else, and we go back to the previous state. And so that's how we build up a stack. This is great. Now, channels are not a new idea. They date back to 1978. Tony Hall looked at this, and he gives us the answer. What we have is deadlock. When there is no specified behavior, this behaves in the language of communication sequential processes, CSP. This behaves like stop. In other words, this is a computation that will run until eternity. There is nothing here that you can ever wait on, or rather you will be waiting in vain and forever. And that is an acceptable answer. Indeed, he formalizes it in CSP. And there was a language a few years ago, back in the 80s and 90s, a language called Occam, which I used. And Occam actually even formalized the idea of stop. It was a keyword. Here is a keyword that will allow you to actually wait forever. Specifically, it can drop you into a debugger. It's a way of forcing a kind of deadlock-like behavior. So how do we test the correctness of this? We're all about testing these days. So how do we test it? Again, Tony Hall, Dijkstra, and Ole Johan Dahl, structured programming. Here we have the answers. Program testing can be used to show the presence of bugs. Yes, but never to show their absence. Damn it. Yeah, we have a limit here about, again, knowability, which is something we're coming back to in the other items. So let's try and test this. We've got 2 channels for pushing and for popping. And what I'm going to do is I'm going to say, if I pop and I receive a value from an empty stack, if pop is successful, in other words, if we do not block, then we fail the test. So now we have the interesting question of like, okay, that's a failure scenario. How do I succeed? Basically, I need to wait forever. If we successfully find ourselves at eternity, at the end of time, and we have not popped a value from an empty stack, then the code is correct. Right, not every question has an answer. What do we do in practice? There is no eternity, there is no time dot eternity in Go. What we do is we pick a suitable value, we call it a timeout, and we say, if it fails that, then it's then we're done. What we have just done here is we have solved the halting problem. Can we, in advance, know whether a piece of code, an arbitrary piece of code, will ever terminate? Yes, you can. That is the answer. That is how you solve the halting problem. You solve it by having a timeout. You solve it by adding non-determinism. You basically say, we will either get a result or we will get a failure at a particular point in time. That is how you solve the halting problem. That is why timeouts exist. People don't tend to think of them as being a solution to the halting problem, but that's why timeouts exist. We don't normally encounter the halting problem. Occasionally we get runaway behavior like that, but normally what we do is we bound things by time. We say, if it's beyond this, we bring infinity down to a limit and we say, not interesting, and that, but we introduce non-determinism in order to solve the halting problem. Okay, now we're into the depths of philosophy. Every truth can be established where it applies. This is an impossible thing. And importantly, it wasn't always believed to be an impossible thing. Indeed, it was an article of faith that then became something that was proven, that then became something that was disproved in 1931. Thank you very much, Kurt Gödel, for your contributions to making the world a less certain place. Basically, the assumption was, we can know this stuff. Everything is ultimately decidable within a formal system. And indeed, Bertrand Russell and Alfred North Whitehead demonstrated this in 1911. As Adrian Collier observes, they published Principia Mathematica with the goal of providing a solid foundation for all of mathematics. This was the era in which we finally had the answers to all of the challenges that had been set. The idea in the Victorian era that everything can be known and knowable, everything can be mechanized, we have the answers to everything, the universe is clockwork, and this is all great. And by the early 20th century, we pretty much had this wrapped up. Relativity, yep, that's just a variation of classical physics. It gave us new answers, surprising answers in some sense, but some interesting new answers, special relativity at any rate. We'll get to general in a minute. And basically everything was known. And then along came quantum mechanics and Kurt Gödel. Everything that we thought we knew in the 1920s and 1930s unraveled. Gödel's incompleteness theorems, there's two, shattered, showing that for any consistent axiomatic system, there will always be theorems that cannot be proven within the system. In other words, there are truths that are true within the system, but cannot be shown to be true within that system. It's like, okay, that's great. This is a kind of, this is the kind of stuff that is the stuff of great books and philosophical contemplation. What does it mean for everyday software development? Surely this doesn't apply. Now, this is a classic book. I've ended up getting two copies because my first edition, well, it's not a first edition, but it's not a first printing, but my copy of the first edition is so well thumbed, it is falling apart, and that's what's on screen. So I've got a more recent anniversary edition a few years back, absolute classic. But he explores, Douglas Hofstadter explores a number of these things. And he says, look, all consistent axiomatic formulations of number theory, which includes pretty much computer science, include undecidable propositions. And it's that undecidability. That's the tricky bit. Can we demonstrate this in a piece of code? Well, let's try this one. How long is a piece of string? Now, I could do this in a number of different languages, but I want to cut to the chase because otherwise you have to create some very arcane and bizarre situations in some languages. I want a language that's going to give me undefined behavior like that. So I'm going to use C. C already surprised us with time travel. So let's just do the humblest thing. For those of you not programmed in C, I will walk you through it. What we have here is strlen. This is a function that was written during the Great Vowel Shortage, where basically you did not end up with long names. And so strlen will calculate the length of a string. It is given a pointer to a sequence of characters that are unchanged. So S is that pointer, and it returns an unsigned quantity. Okay, that is used for size. So that's just a type def in the library. So how do we implement it? Well, the way we do it is we start at 0, we count up. I'm actually borrowing the implementation. I think I've written this implementation straight out of Koenig and Ritchie, C programming language, 2nd edition. If I'd written it, I'd use slightly better names, but let's just be traditional here and use S and N. And what we do is we keep on looping. until we encounter the null character. Okay, so C strings are null terminated. There is a sentinel value and we look for that. And basically we increment until we hit that. That's great. And then we return it. This is easy. Okay, let's bring in a little bit of formal thinking here. What's the precondition to this? For strlen to terminate, for strlen to give us a value that is correct and consistent and all the rest of it, what must be true before we call it? Well, a very relatively trivial one is to say that that pointer must point to something. It cannot be null. Okay, so we're done. We've got a precondition. It's like, actually, no, we haven't. And it turns out that the precondition is a lot more complex. So I'll write the precondition here in gray. There's a reason it's in gray. Basically, what this says is there exists an n such that S of n is null. In other words, basically, there is a null terminator out there. And more importantly, that the interval between the starting point and wherever, let's keep this on screen, wherever that is, between the start and the end, all of that is defined. In other words, we're not dealing with garbage memory. Now, the reason this is in gray, and the reason I've used a back to front E and an upside down A and the set membership E or epsilon style is because, and the words is defined, is because you cannot say this in C. This is a truth of the system that cannot be established at this point. In the system of strlen within standard C, it is not possible to actually check this precondition. This truth must be true for this to work, but there is no way that I can actually prove at this level that this works. This is why preconditions do not give us the full answer. Some people kind of fall in love with the idea of things checking preconditions as being the answer to co-correctness. And that is a fantasy, and it has been a fantasy since the 1930s. And it's not just a limitation of programming languages, it is a fundamental concept. Now, of course, we can change our scope and say, well, what about the calling scope? That's great. But the point here is strlen doesn't see the calling scope. I can prove the correctness of this by looking at the calling scope. At this point, and this is actually how you deal with Gödel's incompleteness, there is basically you move one level out. Something that cannot be proven in this system can be proven in the next system out. But this also has a Gödel statement that is true but cannot be proven, and you keep having to move out and out and out. It's kind of turtles all the way out in that sense. So here I've got a string, be excellent to each other, just general life advice, but also we as a family recently rewatched all the Bill and Ted films. This string is well defined, and when we run it, all of that gobbledygook translates to be excellent to each other 26. In other words, that string is 26 characters long. Okay, and that's well defined, and I can demonstrate that because the S is by definition in the system of C is well defined, and it will have enough characters, and there is a null on the end. Now let's look at a couple of cases where that's not true. If I do this is actually compiles, although sometimes you get a warning for it. S5, you might say, well, look, bogus has got 5 letters, 5 characters. Yeah, that's fine. What about the null? Now, are you feeling lucky? I mean, on a lot of systems, when you run this, it'll actually run and it'll give you 5, because it turns out there's a spare bit of memory there because 5 is an odd number. So you're going to normally get this rounded to a word. So there'll be either 8 bytes available or 16 bytes, and they will all be pre-zeroed. So it works by coincidence. But maybe it works, or maybe you find yourself in deepest, darkest space on your way to M87. It's undefined behavior formally. That's why I put it in red. Even more rigorously here is that S is uninitialized. Modern languages tend to say, you know what, you shouldn't do this. I'm not going to let you compile it. Dynamic languages have a slightly different opinion. They tend to say things like, oh, you know what, I'm going to dummy up a value for you. But the key thing here is that in trying to find what is at the other end of this garbage value, you will come face to face with M87. It is technically undefined behavior. If it works, that was by coincidence. The point here is that we cannot demonstrate within the smallest system of C, such a trivial function cannot be shown to be correct from within itself. Does this have other implications? I mean, I'm not just dealing with edge cases of C. This is a deeper aspect of philosophy that actually, I mentioned machine learning earlier on. It has a number of implications. And the reason I'm quoting Adrian Collier on this and why he cited this is he talks about this idea of fairness. One premise of many models of fairness in machine learning is that you can measure or prove the fairness of a machine learning model from within the system, from properties of the model itself and perhaps the data it is trained on. This is incorrect, and we have known this for nearly 100 years. To show that a machine learning model is fair, you need information from outside the system that you created. This is the bit where machine learning comes face to face with the real world and how people actually interact. We tend to think of machine learning as being big data, but ultimately it is about people. We forget to move beyond that big data and fall straight into that. Now, there are a couple of other cases where this idea of being able to establish a truth at the in the context is also defeated. So people have got up to a lot of strange things whilst during this pandemic and during lockdown. And what you are seeing in front of you is a cartload of Android phones. This was a piece of effectively, I don't know, hacking and art last year. Simon Weckert, an artist based in Berlin, gathered 99 second-hand smartphones and transported them in a handcart around Berlin, walking down the street, and he generated a virtual traffic jam. Because Google Maps determines, basically it says, what it does is it tries to deduce the traffic. You cannot deduce the traffic conditions. You can only, it's not deduction, it's induction that's being used. What it does is it says, hey, look, there are a lot of phones here, that's a lot of cars, and they're moving really slowly. Okay, so he's walking at walking speed. Yeah, that's a lot, that's 99 cars moving at very, very slow speed. And so it shows up as red on a map, and therefore what happens is it then distorts the traffic system in the surrounding streets, because other people who might be using Google Maps then look at Google Maps, go, oh, I'm going to avoid that road, and so on. Now, you haven't actually measured the traffic. What they've done is they've measured the presence of signaling phones, or rather devices that have their GPS engaged. Let's be really honest about what's going on here. In this case, it's phones. Now, why does this matter? It matters because of the way that we drive and the way we drive the economics of the web and the way that companies are evaluated and products are evaluated and the distortions that result from that. Because people keep talking about engagement. They keep talking about engagement. Oh, we're getting better engagement on this. People do A/B testing to check engagement. What does it actually mean? Because I can tell you one thing. We're not measuring engagement when we do that. You are not. There's a lot of things you might be measuring, but you're not measuring engagement. So, of course, as a noun, it applies to two people pledging to get married. But broadly, in this sense, we're talking about the state of being engaged, emotional involvement or commitment. Are we measuring that? Absolutely not. Like Buckminster Fuller said, reality should always appear in quotes. When people use the word engagement, they should remind themselves, we're just kidding. We are looking for a correlated figure. And there is a correlation, but it is not necessarily causal. It's not necessarily 100%. It is not a guaranteed function. You do not get a mapping between somebody's engagement and the behavior that you measure on your server. Okay, that's just facts. You are not measuring engagement. What you're doing may be correlated, but it may not be. What you're measuring is clicks and shares. And that's unfortunately how we've ended up with people having job titles that are about, when I first heard a number of years ago, that people could be SEO specialists. I said, what's that? Oh, search engine optimization. Oh, you're gaming the algorithm to boost something that's not actually intrinsically popular, because the PageRank algorithm that Google originally had was quite straightforward. It was an intrinsic measure of network fan in and fan out. In other words, a basic measure of popularity. I'm not going to say that it is popularity, but it does offer you a simple rank. But what you're going to do now is you're going to gain that. You're going to gain that whole system. That doesn't mean that your page is better, or whatever. We've just created a system where we are rewarding effectively not much more than clicks and shares and clever words. That's not engagement. We've debased human beings to a very simple one-dimensional reward system and created whole companies out of it. So let's look to the future. Here's another impossible thing. The future is knowable before it happens. Well, again, this sounds like this is ridiculous. Of course, this isn't true. I mean, nobody would ever be stupid enough to do this, but would they? I think they would. It turns out that people don't look at that. This is not how it's phrased. What we need to really do, and what we've been doing, is exploring the nature of knowledge. And the great Grace Hopper said, to me, programming is more than an important practical art. It is also a gigantic undertaking, the foundations of knowledge. That basically, it's applied epistemology. You need to know some of this stuff, and you need to classify knowledge. And indeed, as Imo pointed out, let's talk about the unknown unknowns. Let's talk about the known knowns, the known unknowns, the unknown unknowns, and the unknowable unknowns. These actually form 4 of the 5 orders of ignorance that Philip Armour identified. He didn't describe them like this. He described them as 0, 1, 2, 3, 4, and this is 0, 1, 2, and 3, as you see on the screen. 4 was the 4th order of the 4th or the last order of ignorance is basically you don't know the 5 orders of ignorance. So we're not going to deal with that. I'm just going to translate it into the easy stuff. Each order of ignorance corresponds to this. There are things that we know and that we know we know. There are things that we know that we don't know. Okay, I want you to think about any work that you're doing, any kind of customer engagement that you're doing. And when I mean engagement, actually you're talking to the customer, you're engaging with them. There are things we know we don't yet know. And there are things we can immediately identify. Yeah, honestly, we can tell this. Oh, we're going to use it. You want us to use an interface to your existing database. We know nothing about that. Okay, it's not a surprise to us that we don't know. We can tell you that straight out of the gate. Then we have the unknown unknowns. This is where assumptions, I mentioned assumptions earlier on. You don't know that you don't know. Yeah, only when you stumble across it, you go, oh, okay. Yeah, I didn't know that. I didn't even know that I didn't know that. And this is the point that any planning-based approach must account for. It must be a planning-based approach rather than a plan-based approach. A plan-based approach will only take you as far as the first 2. A planning-based approach is the idea that, like, let's keep on going. It's what Dan Terhorst-North talks about when he talks about deliberate discovery. Let us put ourselves in the situation where we are more likely to discover these things. I metaphored in the idea of assumptions being like Lego bricks earlier on. If you've never had the experience of stepping on a Lego brick barefoot, it's not one I would recommend, but if you are bored during this pandemic, then try it out. Your assumptions and the unknown unknowns is a little bit like being presented with a dark room that has Lego bricks on the floor. You know there are Lego bricks on the floor. You know you have assumptions. You know there are things you don't know that you don't know, at least if you have appropriate humility, you do. But you don't know where they are until you step on them. Now, if you stand at the door and never go in, you will never find them. The minute you start deliberately walking across the floor, guess what? You're going to find them. You increase the probability. And then we have the unknowable unknowns. In other words, unknowable unknowns is we don't even know how to find out what we don't know. Ultimately, they do become knowable through time, but we don't know how to find out until time arrives. And even time might not be enough. We don't know. Oh, when's this going to terminate? Well, I'll tell you what, let's wait till infinity and see if it's terminated by then. And if it has done, then it halted. If not, then it didn't halt. But what we're challenged with here, so in other words, halting problem is an example of this, but there's more specific examples. Let's pick on this. Prediction is very difficult. Now, this forms part of this is an obvious issue for anybody who's ever tried to forecast the future. Technology trends. I'm currently reviewing a technology trends paper for O'Reilly, and I kind of put in a couple of things going like, well, we keep predicting that this is going to happen. I don't think this is going to happen. It's a difficult business, but prediction is very difficult, especially about the future. Now, I love this quote. What I also love is we don't know who actually said it. I prefer to think of it as Niels Bohr, and I've always thought about it as Niels Bohr. My co-authors, when we published patent-oriented software architecture books, they wanted to quote Yogi Berra rather than Niels Bohr. The things we don't actually know, and that's the past. So this is, whenever people say, oh yeah, we can know this, how hard is it to predict the future when we can't even predict the past? It turns out that this is surprisingly difficult. Now, this always bugs me. The thing that bugs me the most about this one, and I've kind of said it on and off the last few years, but I'm really making a point about it now because I keep hearing the word roadmap, not just in a technical context. People keep talking about roadmaps and the pandemic. They keep talking about a roadmap, and you can draw a roadmap. But I decided a few months back, I'm going to go onto Twitter because I'm sure that I'm sure people have come up with roadmap templates. Oh, good heavens! Type in just roadmap templates, or project roadmap template. There are loads, and mostly they look like this. Nice wiggly road, you put your text in here, it just makes your PowerPoint look a little more exciting. And I've had a real issue with this because whenever people draw up a roadmap, how many roads do they put in? And look across all of these things online. One road. That's not a roadmap. This is where I live. I live in Bristol. This is what a roadmap looks like. It has a lot more than one road. There are multiple parts. There are possibilities. If one thing gets busy, perhaps somebody's walking down the road with 99 red Android phones. If somebody's walking down the road with 99 phones, then maybe I take a different road. Whatever. The whole thing there is roadmaps are only of interest if you have more than one road. So when people stand up there wonderfully saying, hey, guess what? Here's our product roadmap. No, it isn't. That's just a straight line of predictions about the future that won't come true. Why don't you show me the roadmap? That's a much more honest, and that shows you understand your subject matter. A product owner who stands up and shows you one line does not understand their product. They don't understand the customer, they don't understand the development. An architect that stands up and draws one line does not understand software architecture or development. You see this goes on. Show us the possibilities. That doesn't mean those are all the possibilities, but acknowledge, it could go this way or that way. Just show us a couple. Just show us that there is a space, there's a set. Okay, set-based thinking rather than point-based thinking. And it was quoting the Mike Tyson one, actually, that everybody has a plan until they get punched in the face. And I think that's that getting punched in the face is a wonderful point about predicting the future or failing to. But there are a couple of these roadmaps that really caught my eye when I did my Google search. I want you to look at this one. Hey, guess what? Just fill in the years. Yeah. What were your predictions for 2020? Did anybody get, global pandemic on their list? I don't think they did. That's how, this is the point. We need to approach this with humility. Now you might be saying, yeah, this is okay, Kevlin, I understand. I see you making some points. Yeah, you're right about the roadmaps. Yes, actually, we should be more honest and we should chart out possibilities. Okay, that's actually what makes the endeavor more meaningful and shows that we are competent in our subject matter. But we've got to watch out for some of the buzzwords. There's this phrase, it's been doing the agile rounds for nearly 2 decades. Prioritized by business value. It's become an article of faith. How do you prioritize your backlog? Oh, we prioritize it by business value. I'm here to tell you, you don't, you can't. You're prioritizing it by opinion. You're not prioritizing it by business value. I mean, first of all, let's leave aside the question is that nobody ever says what business value is. It's one of the vaguest terms I've ever come across. For whom is this value and over what time frame? Is it short term or long term? Is it financial? Is business value the same as value of, is it going to help the business stay in business, or is it just giving us a short term boost? Does that mean it's good for the team? Is it good for the customer? What about the customer? Is it their business or our business? In other words, it's not that you can't define it, it's just nobody does. So first of all, if you're going to use phrases like, oh, it's business value, tell me what you mean. Business value is a weasel, is a pair of words put together to pretend it has meaning. It could have meaning, just define. Business value, oh, what we mean is the next quarter financially. Right, that is a concrete definition. I can work with that. What we mean is of skills benefit to our employees. It's a different set of values. What we mean is that the customer is going to receive a benefit that should appear over a 12-month period, and they will benefit in a quantifiable way. And here is what we mean by that. It's their business, not our business. Okay, right. The point here is if you use the phrase, if you use weasel words like business value, expand them, expand it and qualify it. But that's actually not what I'm objecting to here. Or it's only part of what I'm objecting. There's something more fundamental. You cannot prioritize by business value. And I'm not just telling you that it's not a good idea. I'm telling you that it's not possible. And basically the laws of physics forbid you to prioritize by business value. Of course, if you can travel in time, then yes, you can prioritize by business value. But you don't know the business value of that feature you're putting in. You cannot know that business value because it is an unknowable unknown until a particular point in time in the future arrives, and you can say, you can look back and you say, oh, you know what? Yeah, this was worth a lot to the company. Or, you know what? That didn't really pan out as we expected. It didn't have much business value. That is why you cannot prioritize by business value. You do not know it, and it is unknowable without a time machine. What you can, but yeah, Imo's wrong. Yeah, Tom, he can measure. So observation here. Tom Gilb talks about dealing business value. Yes, you can measure business value. First of all, if you define it. If you don't define it, then no, you're doing it by opinion. Secondly, you cannot do it in advance. You can only do it over elapsed time. Everything that's based on the past and the present is potentially knowable. Anything based on the future is not knowable, and that I can definitely tell you Tom does not cannot work around. You can only prioritize by estimated business value. Even if we tick all of the boxes, you can only prioritize by estimated value. So therefore, when you use this phrase, stop your colleagues using prioritize by business value. If they're using it, stop yourself using it. Use the word estimated. It's a constant reminder. Guess what? It's an estimation. We have so many debates about estimation. It's amazing we've completely overlooked this. It's as if it's an untouched and unquestioned thing. Oh yeah, estimation of time for effort, but apparently we never talk about business value estimation. Well, that's what's happening. It's an estimate. And to be honest, most of the time it's just an opinion. It's not even an estimate, but this is as good as it gets. Now, of course, changing the way that you do things, Grace Hopper observed, humans are allergic to change. They'd love to say we've always done it this way. I try to fight that. That's why I have a clock on my wall that runs counterclockwise. You know what? I was so taken with this quote a number of years ago that I thought, you know, I live in the internet age. I wonder if I can find a clock that runs anti-clockwise. Yeah, this is my clock. It messes up my kids somewhat. They can barely read an analog clock, and then they walk into my office and go, Dad, that's just messing with the little that I already knew. So 2 to go, then we're done. Questions, football. A distributed system is knowable. Given we're talking about knowledge and being very specific about it, a distributed system is knowable. And in other words, we can know everything about it. And we can make predictions about things, and we can know stuff about it, and that won't affect our data. Yeah, you know what? It does. It's the classic quote of what is a distributed system is the Leslie Lamport quote. A distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. And 2 years ago, the California fires led to this rather embarrassing incident for my publisher, O'Reilly. Fire in California, can't read your ebook in Pennsylvania. Yeah, perfect demonstration of what Leslie Lamport was talking about. But that's a kind of a nice pithy kind of saying, but we can actually formalize it. This is Brewer's theorem, Eric Brewer, but probably better known as the CAP theorem. And it actually is a theorem. It was originally described as a principle, I think, in 1999. Then it kind of like conjectured up to be a conjecture, and then it was actually proven kind of nearly 20 years ago, I think. So it is actually a theorem. And so CAP, no reference to the MCU. Consistency, availability, partition, tolerance. You can have 2. You cannot have all 3. Consistency. When we're dealing with a distributed system, let's just focus on the data for a moment. And clearly there's messages and so on, but let us make it data centric. So basically I'm thinking of data as read and write. My messages are requests for reading or requests to update a value, to write it. To be consistent, every read operation receives the most recent write. Everybody sees the same value, or they get an error. Okay. Availability, you can actually start thinking, wait a minute, isn't this kind of related to what Kevlin was talking about earlier on with kind of time availability on a system? Yeah, it is kind of. Availability is every request receives a response. You always get a response. a non-error response. You always receive a value, but you don't get the guarantee that it's the latest value. And then partition tolerance, slightly formal terminology. Partition basically means I have a network, a router goes down, now I have two networks. Okay, it's been partitioned. Can my system continue to function when this is when the network is partitioned? Do we still have a running system, or do we have partial failure, or even total failure? But actually, partial failure is normal. That's the thing. Partial failure is a norm in distributed systems, whereas total failure is something we're used to with sequential localized programs. Now, the point is you can have any two, but not all three. You can have everything receives the latest value or an error, and you can still have the system continuing to run. And so therefore, when you get partition tolerance basically now means, guess what? I can't give you the latest value. Okay, but at least you know. But you're not going to get very far. Okay, well, what about availability? Right, availability, let's do it this way. You're always going to get a value, but if the router goes down, I'm just going to give you my latest cached value. I can't tell you if that's actually the same as what the other side of the network is getting. We can have two different views of the value that are not the same in the system. But it won't be consistent. Right. In other words, you can have the, and of course there's this case, which some people say is not useful. Yes, you can have it to be consistent and available, but you don't get partition tolerance. Actually, that's the edge case. That's what you have in sequential programs, sequential local programs, non-distributed programs. Effectively, this is kind of like a Heisenberg's uncertainty principle for a distributed system. And it's time for Douglas Adams, Hitchhiker's Guide to the Galaxy. We demand rigidly defined areas of doubt and uncertainty. We have them. Now, the problem is, what this has led to is a little bit of laziness on the part of a number of developers. I often find when I'm using certain apps that I will see one number and then I will see on the same screen. So, you know, I've had this with Gmail in the past. It'll say showing 1 to 11 of 10 emails. Okay, yes. So there's a couple of things there. One, yes, I don't have thousands of emails in my inbox. I use my inbox as an inbox. People that don't use their inbox as an inbox and have thousands of emails, they frighten me. I'm going to say that just, you know, just a personal discomfort, and perhaps the social isolation from them is no bad thing. But how can I end up with 1 to 11 of 10 emails? It's showing me 11, but somehow it's got the number 10 stuck there. And sometimes people say, oh, well, that's to do with eventual consistency, which is a natural consequence of this. Okay, it's the idea that ACID transactions don't really work without non-scalable infinite and locking everything. In other words, they basically do not scale and they are problematic. It's not that we don't have any value for them, it's just that that's not what we should assume our data quality is. And we end up with base semantics. Okay, we end up with eventual consistency. Eventually, everything converges on the right. And people use that as an excuse for why you're getting garbage on your screen. 1 to 11 of 10. I've had it with loads of social media applications. And people say eventually, no, that's absolutely not the case. The distributed system may not be in a consistent state, but this is code in the same client. This is the bit we do control. There is no uncertainty. If you've got one field that says 11 and another field that says 10, there's a technical term for that in software. It's a defect. You've got inconsistent data in the same address space on the same machine. Okay, that's running on my browser, and that's just bad programming. Okay, or poor programming if I don't want to be too judgmental. But it's that time of the evening I'm feeling quite judgmental. So the last one, okay, let's make it less philosophical. Technical debt is quantifiable as financial debt. Okay, no, it isn't. Plain and simple. It's a metaphor. It reflects an idea in its common usage. Common usage, Meyer Lehman back in 1980 observed, as an evolving program is continually changed, its complexity, reflecting deteriorating structure, increases unless work is done to maintain or reduce it. And we have employed a number of metaphors to try and get our heads around this. A particular metaphor that has caught our imagination and our vocabulary is technical debt. And Ward Cunningham came up with it in 1992, or rather he came up with the debt metaphor. He didn't call it technical debt. the name technical debt actually emerged later in the 90s, and really and I know I was using it, it was on the c2.com wiki, but it was really down to Martin Fowler who popularized it. By that point, people were by default calling it technical debt. Technical debt is a wonderful metaphor developed by Ward Cunningham to help us think about this problem. Like a financial debt. Right, okay, so here's our metaphor. So Imo is talking about the concept of software entropy. I've actually got a whole talk where I talk about all the various metaphors. Entropy, yes, I loved entropy. My first degree was in physics, then I went into programming, and I thought, oh, this makes a lot of sense. If we think of an information disorder and entropy, I thought that's brilliant. And then quite literally, you have to put work into a system in order to sort of introduce order. And I thought the metaphor was perfect. The problem was that most of the people on the team hadn't got a degree in physics. And it turns out that the value of a metaphor is in its one of the values of a metaphor is its ability to communicate the idea. And it turns out, yeah, that's not such a good one. If you find you're having to explain, if you're having to, a metaphor is a mapping. And explain this thing that's quite difficult to understand or is novel in terms of this thing that you already know. If I also have to explain this thing, then it's not going to be a good metaphor for that audience. You might find the right audience, but you might not. So if you're using 2 hops to explain it, then that is a problem. Debt, however, is something that everybody has a handle on. And that idea, debt incurs interest payments, which would come in the form of extra effort that we have to do in future development because of the quick and dirty design choice. Now, there's a bit of a judgment here. Quick and dirty design choice was not originally the way that Ward framed it. He actually looked at debt as debt. Not all debt is intrinsically bad. Of course, our common experience, and certainly the published and public experience of debt, is very negative. But debt plays a role. That's what he was trying to emphasize. He was saying, yeah, there is bad stuff, but that's why you've got to repay it. He kind of assumed that if you told people, hey, this is a debt, they would do the right thing. But that's because Ward's he's a really nice guy and he keeps his finances in order. For some people, it's just like, it's debt, whatever. Particularly companies start up using venture capital, they regard themselves as burning through money as being a sign of progress. Running up debt is a good thing. So when you tell them, hey, guess what? You've got more debt. They go, excellent, we're doing really well. Exactly the opposite of what they should be thinking. But the intention of the debt metaphor was to allow you to reason justifiably, in a justifiable sense, about the kinds of problems you might be encountering. And whether or not you're making a wise choice. So for example, my wife and I have a debt on a house. It's called a mortgage. That's structured. We know what we're getting. And it's well defined in terms of our ability to control it. Yeah, it's good. It's not, so it's not intrinsically bad. But when people say debt, it has many negative connotations, and that's what's clung. And you can even see it in Martin's phrasing, although he probably didn't mean to bias it this way. Quick and dirty is never a positive thing here, design choice. But the other thing I keep having to drag people back to is it's a metaphor. The word metaphor is really, really important, because I find people have set up whole dashboards on hang on, let me just go through. So yeah, the questions box is not very helpful. Tom has put up a link. Hang on, this is a nightmare, this UI. Okay, let's see if we can adjust that. So got a few things here that I do think there's a very, very narrow window here that is quite challenging. But I realize more questions than I had assumed have come down. So
I wouldn't worry too much. I mean, many of them are just comments, really, and the rest of us can see.
Yeah. Yeah, as a meteorologist, yes. Impact estimation tables, yes. So nice contribution. Real time, all the rest of it. Yeah, incremental feedback. That's the point. You can adjust your priorities, but you're always doing that with hindsight. It's always based on the immediate past. You'll never do it, but it is always estimations. And that's, we're navigating based on the latest information. We're not navigating on information that does not yet exist. Important thing. However, let's bounce back to the idea of metaphor, because I see people, and there are various products out there on the market that will show you your technical debt in your code, as in they will give you a number that is in a currency value. And it's just like, no. Actually, that's not it at all. That's not what the intent is. Metaphor is not identity. Otherwise, if we found the perfect metaphor for technical debt, software entropy, and so on, then it would no longer be a metaphor. The reason a metaphor is because it is not a perfect mapping. The minute it becomes perfect mapping, it is an identity. So I found, last year I observed, found myself cautioning against the category error of treating the technical debt metaphor literally and numerically, converting code quality into a currency value on a dashboard. This, when I kind of challenge people on this, I've sort of said, how do you know that this piece of duplication is worth that amount of money? Where did you get the number from? And either they've trusted a tool, you don't know and this is the worst thing, people fall for precision. So, this is going to be £10, that's going to be €20, that's going to be, it's like, no, you don't know that, you're just making numbers up. And we see enough of that in the political realm, we see enough of that in the business realm. The point is, I can point to this piece of code and say, there is duplicated code here. I cannot tell you the financial impact of that piece of code. Some people get back to me and they say, oh, no, we've estimated it. We've gone through all of our technical debt and we've estimated how much effort would be involved in removing it. So first of all, it's a debt estimate. It's not actually your debt. It is an estimate of debt. And it's actually not actually a debt, even an estimate of debt. It is the cost of repaying. And that is a category error, because as Martin makes clear and as Ward makes clear, it's not the cost of repaying the debt, it is the cost of owning the debt. It is not how much work, and that's the key thing. I wrote a piece for O'Reilly last year on exactitude and technical debt. The simple message of the technical debt metaphor, it is not simply a measure of the specific work needed to repay the debt. Even if we could estimate that to high fidelity, that gives us a number, but that's not the technical debt. Technical debt is the additional time and effort added to all the past work, the present work, and the future work, and we know about the future, or we've learned about what we can't know about the future, that comes from having the debt in the first place. That is the metaphor. It's not something else. It's not actually the financial cost that you have to repay, that you can quantify now and will repay. That is not what the technical debt metaphor was about. This terminology may be useful. How much work do we estimate to eliminate technical debt? But that is not the technical debt. That is the work to eliminate the technical debt, and that is subtly different. So that brings us to 0. Now, I meant to finish about 10 minutes ago, so you get a bonus one. Things that are impossible, finishing on time. So apologies for overrunning on that one. Okay, so we have a few minutes for Q&A. Although I don't know if people can unmute their mic, or if they can use the chat, because the visualization in the questions box, although I can see it, is not great. No, hang on, I've got it. I've now readjusted it, and yes, it's not good with screen sizes, I'm discovering. So I have to use my low resolution screen. But there we go. Yes, okay, right, fine.
I've also enabled everyone to unmute themselves if they wish to ask a question directly.
Yeah, okay. Thank you very much for your comment, David. And also your comments and the link as well, Tom. Any other kind of thoughts, questions, reflections, where this takes you, where it doesn't take you?
Well, I just want to come back to the very last point, which is from technical debt. Yes, I mean, financial debts in the real world need to be serviced, and I think that's the metaphor actually works pretty well, because as long as you've got the debt, you've got to service it. That's an ongoing cost. So you then have to weigh up the cost of paying the debt back alongside servicing it. Which would you rather have? as far as the national debt. So, and we seem to be borrowing yet more to pay, to service the debt.
And that's where we get, as it were, misdirected by our metaphor, and that's where the negative connotations come from. But importantly, it's that idea of when we look at debt, it's a complex financial instrument in the real world. It turns out that's the same applies to code. We like to oversimplify things, but importantly, the debt of the code is not a financial debt. In other words, if I owe you £10, then I owe you £10. If I owe you £10 with interest, then I owe you £10 with interest. If I've got a piece of duplicate code, then I owe you a piece of duplicate code, but that is not the financial quantity. That becomes a derivative. So in other words, there's an off by one that we start off with as well. Now we are one level of indirection removed at best. So we've got to get the concept right, then we've got to get the indirection, and then we have to recognize everything's estimation. So when somebody says this duplicate code, you know what, it might not have any impact at all, or actually it might do. We end up with that kind of interesting uncertainty. But what the metaphor, if we understand it as a metaphor rather than as a literalism, then it actually is helpful. You've got to service the debt. You've got to make judgment calls on what are we going to do with it now, and that's what it's supposed. That's the behavior that that Martin and Ward were originally trying to invite people to think. That's what a metaphor is trying to do. It's trying to help you think like that. It's not trying to get you to reduce things to things that have ISO currency code by them with a number. That's not what they were trying to get you to think.
Right.
Any other reflections, interactions?
Muted himself. So Chris, go ahead.
I'm going to stop sharing my screen just so you've got a little more real estate.
I'm going to share a couple of thoughts. Thank you, Kevin. A lot of your ideas kind of hark back to my kind of training as a mathematician. So I'm very pleased to see you kind of condensed them down into real-world experience of programs. The two things I've kind of learned is one is in terms of recovering from disasters and trying to plan things that go wrong, the unknowable and not the unknowable. Well, some of them are unknowable and some are just unknown. It's basically three things at once kill you. You have a contingency plan. You can kind of cope with it when something goes wrong. Two things go wrong at once. Each got a contingency plan. You can sort of fudge it. Three things go wrong at once, and you get the 3 Mile Island, which
Yeah.
My example of work was computer room on the 3rd floor had a 50,000 gallon flood.
Yeah.
Which came through the ceiling. That's not something we planned for.
Okay, I don't think all of us heard the question because it's very quiet. If you could just summarize.
You might be far from the mic. I'm just struggling.
Oh, sorry, my microphone. Yeah, sorry, I had my headset. I'd moved my microphone out of the way to have a cup of tea.
I hope the cup of tea was good. But I think one of the things I heard you say was that the way that I sometimes phrase it, you cited, one thing going, contingency plans, but one thing going wrong, two things going wrong versus three things going wrong. These are very, very different concepts. Yeah. In terms of how their knowability, and it's what I often describe. In particular cases, I often use the Knight Capital example from 2012, when Knight Capital accidentally spent 45 minutes giving their all of their assets away through a failed server upgrade, and that was an example of redundant code. Or rather, no, redundancy is a formal term, but it was an example of dead code that had come back to life, and so on. And this was the interesting thing, is that I always describe it in very much the way you're describing is, it's not the problem did not happen because of this or this, it happened because of this and this. And so therefore 3 Mile Island was this and this and this. It's kind of like these things together, and that challenges us as human beings, and our way of approaching the world, which is a relatively simple, it's based on simplification. And in software, we regard simplification as an art. The problem is that sometimes we accidentally project that back out onto the world. It's an art of design, but then we project that back out of the world and see the world perhaps a little simpler than it really is.
Yeah, and actually, as a meteorologist, we've been approached over 30 years by all sorts of people about intelligent systems, expert systems. Can we find a quick using AI, machine learning to improve weather forecasts? And the problem is exactly as you said. With the machine learning, you've got a training set, and within the system, you can't predict the things that occur that are extreme. And
Yes.
we've learned that from experience. The equations, Newton's laws of motion, force equals mass times acceleration for a thin fluid on a rotating sphere with a load of other bits and pieces, including thermodynamics, are solvable equations. And the more accurately you solve them, the more precise the answers, and usually more accurate the answers. But we find the name of the game for us is not forecasting the mean. You're trying to forecast the extreme events. They're the events that are dangerous, and the learning sets just don't do that.
Yeah, and that's the thing. It's the standard thing with machine learning. There's a standard joke with machine learning is that machine learning system walks into a bar, and the barkeep says, "What are you having?" Machine learning system says, "What's everybody else drinking?" It's very much that. It's very much. It's kind of like it's about finding a mean, sometimes where the mean does not actually mean anything, interestingly enough, about finding some kind of average rather than the outliers, which are the things that are interesting. And I can't remember which statistician or economist said that the average is a very dull statistic sometimes. It's not the one you're interested in.
Yeah,
well,
on
yes,
average, we've all got, on average, we've all got one testicle and one ovary. Right?
Yes, indeed. Yes, there's Hans Rosling's a wonderful observation about the average number of legs per person in Sweden is around 1.9999. Because there are some people that have 0 legs and 1 leg, and that pulls the average down. If you look at the mode, then that's a different answer. But yeah, we get all these kinds of things. So let me pick up on Verity's question.
Yes, please. I was going to precisely say that.
Yeah, might not be quite related, but would I have any tips on how to approach this when talking with non-technical people, e.g. managers? Like they see you as being slow because they don't understand that you can't run faster on just a 5-minute job because when it's because of technical debt. Yeah, you see, I tend to think of these things. There's no silver bullets here. What is manager speak? We find that managers come in a variety of shapes and sizes and backgrounds, knowledge, assumptions, and pressures. Again, organizations are a manager in one organization and a manager in another organization may actually be under completely different work assumptions and pressures. So I think, again, there's no fixed answer here. So I tend to think that what you're doing is it's more like a dance. There's it's an improvised ad hoc choreography. What you're doing is you're looking for the right language. You're looking for the right terms. And perhaps with one group, a particular metaphor works. In fact, Ward Cunningham came up with the technical debt metaphor because he was talking to a finance firm. That he was trying to explain why it made sense to do certain things quickly and why it made sense to then spend time. We can get a market advantage with this, but then we've got to pay back that debt. He wanted to speak in their language. What we've done is we've lifted that and tried to use it with everybody. But as I've said, people have different responses to debt. So I don't think there's a fixed answer thing. I think this is a process. In other words, it's an ongoing process. You're always trying to figure out what's the best way to explain this. How do I communicate this? And I think there's a constant process of experimentation. You may find even in the same company something that works well. In fact, this is terrible because I had a really long conversation with somebody about this a few months ago. They had said technical debt, I'm not a fan of it, but in our organization we have shifted to using another terminology set, and he's in the medical device sector, and it makes perfect sense. It's their language and it works. And so, in other words, although technical debt is not the end, it's not the destination for a conversation on metaphors, it's a starting point. It shows that you can be quite creative. But if it's not working, then we should not keep using it with a particular people, or rather, if it's washing over them and it doesn't move them, then perhaps we need a different way of thinking. And sometimes that's kind of like a process of exploration. What else shall I try with this person? What other ideas have we got to try and communicate what is effectively a very abstract idea? The thing that we can't, you know, software is not kickable stuff. I'm sure we wish it were at times. It's not kickable stuff, and therefore our senses are not well tuned to it. Our senses are geared to the physical world. Therefore, we will always be talking in abstractions. And to talk about abstractions of abstractions is quite obscure indeed. So when we try and relate our work, and time is the most obvious piece of physics that does come out of all of this, how we consume time, then it's not surprising it's difficult, and that we're not always hitting, as it were, the right message, because I think it's a search process. So that's not the answer that you wanted. I'm sorry I don't have a better one, but I've kind of come to believe that it's very much when, to go back to your question, how to approach this, approach it, regard it as an approach, regard it as I'm going to try this, I'm going to try that, be experimental, have a roadmap with more than one road, and that applies to your terminology as well. Anything else we want to, well, so thank you very much. Yes, Ian points out, sometimes when we improve code and produce a great result, we may feel like we have transcended the law of entropy, and that's a great feeling. But as you observe, we've just put in the energy to compensate. That we've made the system ordered through work, quite literally in that case. You know, it might be a fight against the ravages of the chaotic machine, but it's still, you know, it's still overall in the larger picture of things. It's like, yeah, maybe not. Right. Yes. So, Chris, thank you very much. 4 minutes to kick off, and that gives me just enough time to say thank you very much. I hope that has been thought-provoking. That's what I want to do here. I'm not sure I have answers, but it perhaps offered you a little bit of distance between assumptions and the way you look at them, but also perhaps shaken a few things up and go, oh, I've never looked at it like that. Taken ideas you're familiar with and, as it were, defamiliarized them and showed you a different perspective on them, and caused you, as it were, a different avenue down which you can ask questions or frame your conversations. So I will hand back to Imo at this point.
I'm really grateful to you, Kevin, for sharing your thoughts with us, and I'm going to have to look over the recording of this session and remind myself of some of the things that you said, because there was a lot of ideas there. It's certainly shaken me up quite a bit, and I hope that those who are still on the call are going to come back on August the 5th, and hopefully before then we'll find a very entertaining and interesting speaker.
And just as a general point, if you've got any follow-up thoughts and whatever, you can find me online. My name is sufficiently internet unique that's not a hard thing. Twitter, LinkedIn, whatever. In the meantime, have a good evening.
Good night.